Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic we're going to discuss vectors orthogonal to a given vector. So in this topic we are going to find all vectors orthogonal to a given vector, that is, all vectors that are at a right angle to a given two-dimensional vector, and then we're going to apply this to finding all points that satisfy the equation of a line. Now, a quick review. Recall that given two vectors u and v, the inner product between these two vectors is given as the product of the first entries plus the product of the second entries. This may be written sometimes as u dot v, and it is sometimes called the dot product. Now, given the vector u is equal to 4, 3, what are all vectors that are orthogonal to u? Well, let's do this from secondary school. Notice that if v is orthogonal to u, then the inner product of u and v must be 0. But the inner product of u and v is 4 times the first entry of v plus 3 times the second entry of v. Thus, we have a single linear equation in two unknowns. 4 times v1 plus 3 times v2 is equal to 0. Now, given this equation, we will allow v2 to be a free variable. Now, what does that mean? That means that v2 can take on any value we want. The reason we do this is because there are two variables but only one equation. The variable v2 is also called an independent variable because that variable does not depend on any other variables. So in this case, if v2 is an independent or free variable, then we can find or solve for the value of v1 in terms of the free variable. So given this equation here, we can bring the second term to the other side and then divide both sides by 4. Therefore, whatever value v2 has, v1 is negative 0.75 times v2. Now, v1 is sometimes described as a bound variable because its value is bound by the value of v2. Alternatively, it is also called a dependent variable because its value depends on the value of v2. Change the value of v2, v1 must necessarily change. If v2 is equal to 3, then v1 will be negative 0.75 times 3, or negative 2.25. So, for example, given the equation in the top right-hand corner of the screen, if v2 is equal to negative 1, we can plug v2 into that equation to determine that v1 is equal to 0.75, and therefore the vector u equaling 4, 3 and the vector v is equal to 0.75, negative 1 are orthogonal. Additionally, if v2 is equal to 2, then we can plug that into the equation and find that v1 is equal to negative 1.5, and so once again u is equal to 4, 3 and v is equal to negative 1.52 are orthogonal vectors. Significantly, however, if v2 is equal to 0, then v1 is equal to 0, and therefore u equaling 4, 3 and the 0 vector are orthogonal. Now, looking at these 3 points that we found, we see that they appear to fall on a line. Let's try to show that, but we're going to show it using vectors. Now, if instead we don't give v2 a value, but instead we simply place v2 in the second entry, and in the first entry we put the value of v1, which is negative 0.75 times v2, then we know that these two vectors must be orthogonal. Now, recall the definition of scalar multiplication. S times a vector u is equal to s times the first entry and s times the second entry. Now, taking a look at the vector we just found above, can't we factor out v2? So, in other words, is that vector not anything more than a free variable v2 times the vector negative 0.751? Well, actually it is. And so essentially this says that all scalar multiples of v equaling negative 0.751 create all vectors that are orthogonal to our given vector u. Therefore, all vectors that are scalar multiples of our given vector v, which is negative 0.751, which we can see here in the second quadrant, all of these form a line, and every single point on this line, or every vector on this line, forms a vector that is orthogonal to our given vector u. Alright, so now we have found all vectors that are orthogonal to our given vector u. Next, we're going to apply this to the concept of the equation of a line and finding that line. But what we're going to do is we're going to find this in terms of vectors, not in terms of algebra. So the equation of a line, as you know from secondary school, is ax plus by plus c equaling 0, where a, b, and c are given. Okay, they are not unknowns, they have to be given, and if these three values are given, then this defines an explicit line on the plane. Note that a times x plus b times y is an inner product. It's the inner product of the vector u is equal to ab with an unknown vector xy. So therefore, we can replace the ax plus by with the inner product of the vector u and an unknown vector xy. Thus, the equation is this inner product plus c equaling 0. Note that ax plus by plus c equaling 0, to define a line, at least one of a and b must be not equal to 0, and therefore the vector u is not the 0 vector. Now, how do we interpret this value c? Because essentially we are now finding all vectors xy such that the inner product with u is equal to negative c. Well, let's consider this line, for example. We have the vector, the equation, 3x plus 4y plus 5 is equal to 0. Now, in the lower right-hand corner, we have the vector u is equal to 3, 4. From secondary school, you can solve for y, and you can see that this line is the one that is shown in blue. Now, by inspection, one point on this line is the vector v0 is equal to negative 1, negative 0.5. We can see this point on the line in the third quadrant. Note that, of course, we can calculate this inner product. The inner product of 3, 4 and this vector is just 3 times negative 1 plus 4 times negative 5, which is negative 3 minus 2, and that does indeed equal the value negative 5. If we take any other point v on this line, or any other vector v on that line, and we calculate v minus v0, this difference is the vector pointing from v0 to v. Now, doesn't it appear that v minus v0, that vector, doesn't it appear that that vector is indeed perpendicular to u? That is not the inner product of u and v minus v naught equal to 0? So first, let's have a quick review. Recall that the inner product of u and a sum v plus v naught is equal to the sum of the inner product of u and v and the inner product of u and v naught. If you're using the dot notation, essentially this says that u dotted with the sum of v and v naught is u dot v plus u dot v naught. Similarly, the inner product with u and the difference v minus v naught is the difference of the inner product of u and v and the inner product u and v naught. Again, using the notation of the dot product, this is u dot v minus v naught equaling the inner product or the dot product of u and v minus the dot product of u and v naught. Thus, if the vector v naught is a given point on the line that we know of, and v is any other vector on that line, then both of those vectors are on the line, and therefore both of them must satisfy that the inner product of those vectors with u is equal to negative c. That's the definition of those vectors being on that line. Thus, the inner product of u and the difference is the expression on the right-hand side, but both of those expressions must equal negative c, so we have negative c minus negative c, which is negative c plus c, which is equal to 0. Therefore, if we have any vector v naught that appears on that line, then that line is by definition all points or vectors v that satisfy the inner product of u and v minus v naught equaling 0, or all vectors v such that v minus v naught and the vector u are orthogonal. Now question, how do we find that vector v naught? We saw previously that we found that one vector that appears on the line by inspection. We let v1 is equal to negative 1, and from that we deduce that v2 must be negative 0.5. But this isn't an algorithm. This requires human intervention. Is there an algorithm that we can use to find at least one point on that line? Well, notice that the vector u must have a scalar multiple that intersects with the line as seen in the image below. So the question is, what scalar multiple of u gives us the blue point, and if we do find that scalar multiple d times u, then the inner product of u and d times u must equal the value negative c. But wait a second, the inner product of a vector with a scalar multiple of another is just that scalar multiple times the inner product. So for whatever value d is, d times the inner product of u with itself must equal negative c, and therefore the scalar multiple d must be negative c over the 2 norms squared of u. All right, that's easy enough to calculate. Now, in our example, we can therefore find that d is equal to negative c over the 2 norm of u squared, and that's just equal to negative 5, because c was equal to 5, over the 2 norm squared of u, which is just 3 squared plus 4 squared, which is equal to negative 5 over 25, which is negative 0.2. So therefore, negative 0.2 times u is that expression there, which can be calculated to be negative 0.6, negative 0.8. That vector there is the vector or the point shown in blue as a blue dot in the image below. Thus, all points that satisfy the equation 3x plus 4y plus 5 is equal to 0 are all vectors v such that the inner product of 3, 4 and v minus negative 0.6 and negative 0.8 is equal to 0. That is, it is all vectors v such that v minus the vector negative 0.6, negative 0.8 is orthogonal to the vector 3, 4. Now, one thing that's interesting about the v naught that we found with this algorithm is that this is the point on the line that is closest to the origin. That is, it is the vector v naught that is on the line that is closest to the 0 vector. Every other vector on that line must be further away than this point. Now, in general, given the line ax plus by plus c equals 0, then all the points on that line are all vectors v that satisfy this inner product equaling 0. So for example, let's look at this different line defined by 1.8x minus 2.6y minus 4.2. Well, we can now find the one point on the line that intersects or is a scalar multiple of the vector u is equal to 1.8 negative 2.6, and that turns out to be the vector 0.756 negative 1.092. And so therefore all the points on the line given by this equation are all vectors that satisfy the equation here, that is all vectors v such that v minus this particular vector are orthogonal to the vector 1.8 negative 2.6. Okay, in summary, in this topic, we have seen that given a two-dimensional vector u, then all vectors that are orthogonal to this two-dimensional vector u include all scalar multiples of one specific vector v that we found. Also, the equation of a line can be reinterpreted as all vectors v where v naught is one point on that line, then all points on that line are all vectors that satisfy v minus v naught being orthogonal to the given vector u defined by the coefficients of the linear equation. Here are some references, acknowledgements, the colophon, and a disclaimer. Cheers!